Hello, and welcome to Applied Calculus, a Pre-Calculus Review Part 1. This is for business calculus, that sort of thing. My name is Tuesday J. Johnson, and I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Totally forgot my title there for a minute. Alright, here we go. Applied Calculus. So business calculus, pre-calculus review, so a little bit of algebra for you. Let's first start by looking at the real number line. We can represent real numbers geometrically by points on a number line, and we see here we have the origin 0, that's where we start. Positive values increase to the right, negative values, right, the negative numbers will decrease to the left. And we can use integers, we could use whole numbers, we could use natural numbers, we can use rationals, we can use irrational numbers. The only thing we won't see on this particular number line is complex numbers. Now the real number that is associated with a point on the real number line, so like here, 1/2, that's called the coordinate of that point. As we're looking at number lines, we can look at relations between various numbers. For example, we can look at this whole range of numbers, this interval of numbers from A to B, and the parentheses, this is an open interval, parentheses tell us that we're not including the endpoints A and B. So that's choose a number between 1 and 10, but we can't include 1 and you can't choose 10. An example, right here, next to it, -2 to 1 with parentheses at -2 and a parenthesis at 1. I know some people use the open dot, closed dot idea, and the parentheses, also known as round brackets in my head, are corresponding to the open circle. So an open dot, so we would not include it. A closed interval uses square brackets, or square brackets, what I call them. From A to B, now I'm choosing a number between 1 and 10, but it could be 1, or it could be 10, or anything in between. So we do include the endpoints. Including the endpoints in the interval from -1 to 2, the closed interval. I'll put in brackets from -1 to 2, and you can see that the bracket direction indicates everything in between them. So it kind of tells you a direction at the same time. We also have two forms of half-open intervals. It could be open on the left, or it could be open on the right and closed on the other side, and the corresponding intervals that go with that. So intervals is a range of numbers that we're looking at on a particular number line. But don't get stuck in that word range. We haven't hit functions yet in this review, so don't think in terms of functions, just think of in terms of pick a number between. That's what we're looking at with intervals. We could also have infinite intervals, and it could be an open infinite interval where we're going from, say, A to infinity, or a closed interval from A to infinity. Notice the infinity will always have a round bracket or parenthesis on the end, and on a corresponding number line, the arrow would indicate it continues going forever to the right. The only difference between the top two notations is, do we include A or do we not include A? The bottom two, this is from -infinity to A, -infinity to 1, say, or from -infinity to -1/2, but this time we include the right endpoint. Infinities, whether it's positive infinity or negative infinity, will always have the parentheses, the round bracket, and then we just have to determine, can we use the real number or not? Is it an open or is it a closed, and which direction are we going? So infinite intervals, quite handy as well when it comes to calculus. Alright, so exponents. Recall that repeated multiplication can be represented by exponents. So b to the n literally means you take b and multiply it by itself n times. This number b, right, that we multiply it repeatedly, is called the base. And the superscript n, the number of times that we multiply it, is the power or the exponent of the expression. Now for b values that are not 0, so any number other than 0, b to the 0 equals 1. Now hopefully you're thinking, well, what's 0 to the 0 power? That's where we need calculus. We'll get there by the end of the semester. The nth root of b, also a power of b, is written as b to the 1 over n. And this denominator becomes the index in radical form. So the index and the denominator are exactly the same. b to the 1 over n is the same as the nth root of b. And we have the property that b to the 1 over n, all raised to the n power, is b. And we're going to see a couple of properties that explain to us why that is here in a couple of slides. I think the next slide. All right. By the way, I just want to throw a little shout out here. I did take these from Tan's Applied Calculus textbook. I honestly don't remember which edition, but provided instructor resources provided by Cengage. So I did not create this. This looks awesome. It wasn't me, but I'm going to use it for you. So if we have an integer exponent, a to the n is a times a times a times a, n factors of a. And here's a little example. 2 to the 5th means I'm going to multiply 2 by itself 5 times. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And we will always simplify our numbers to exponents. Even if it's 7 to the 49th power. That's not true. That's just evil. We would want to try to simplify that if we could. A zero exponent, as we said, 0 to the 0 power not defined, but any other number other than 0 raised to the 0 power is 1. And a negative exponent is like a direction sign. This negative exponent tells me to take it across the fraction bar in order to make it positive. So 6 to the negative 2 is the same as 1 over 6 to the positive 2. Now I know what 6 squared is. 6 squared is 36, and so I'll simplify my fraction. Notice both cases, both the left column and the right column. A to the n, a is going to be a positive value. We do have rules for a being negative values, but they're not something we frequently talk about until you get to higher levels of math. So here we have integer exponents. Let's take a look at fractional exponents. If n is a positive integer, then a to the 1 over n is the same as the nth root of a. Therefore, if you see 16 to the 1/2, that's the same as the square root of 16, which we all know is 4. If you have m and n, which are both positive integers, then a to the power of m over n is the nth root, right? Denominator is the index of a to the m, so it keeps its numerator. Or, a lot of times I'll use the second variation of it, the nth root of a, make it smaller before I raise it to a larger power. So 8 to the 2/3, I don't want to square 8 and get 64 and then have to think about the cube root, when it's much easier to take the cube root first. Cube root of 8 is 2. And then square it. 2 squared is 4. And then if you throw in the negative sign, all that tells you, once again, a direction sign, tells you to take it to the denominator, and we can simplify. Feel free to hit pause anytime you want to look over some of these slides without having to listen to my voice. A few laws of exponents. If we multiply two things with the same base, right, a is the base, we will add their exponents. For example, x squared times x cubed is x to the 2 plus 3, which is x to the 5th. As long as a is not 0, a to the m divided by a to the n will subtract. And it's kind of handy if you use the order of operations. Let's throw that up here. P, E, M, D, A, S. I like this representation because if you're multiplying two things with the same base, you step down and you add their exponents. If you're dividing two things with the same base, you step down and you subtract their exponents. Let's throw in some yellow here. If you have a power raised to a power, so you have exponents on an exponent, you will end up multiplying. And so a to the m to the n power, a power raised to a power, you multiply. Order of operations is a great way of remembering these. We also have the power of a product. AB to the nth power is a to the n, b to the n. And I'm going to rewrite this example. 2x to the 4th power, that is 2x times 2x times 2x times 2x. And what will we do? We'll multiply all of these 2's. When we multiply all of these 2's, we'll get 2 to the 4th. And when we multiply all of these x's, what do we get? We get x to the 4th. And that gives us exactly what it told us there. Same thing, if we have the power of a quotient, it's the quotient of the powers for the exact same reason that I've shown you here. All right, these are good power rules to know. Possibly something to put on a note card if you have a hard time memorizing. Just look at it every once in a while instead of grabbing your phone while you're at a stoplight. Look at the note card, get them memorized. Rationalizing is going to be a big part of calculus. And rationalizing is a fancy term for remove the radical from. So if a radical appears in the numerator or denominator of an algebraic expression, we often try to simplify the expression by eliminating the radical from the numerator or the denominator. In general, it's nearly impossible to completely remove the radical without changing the expression itself. So we'll either rationalize the denominator or we'll rationalize the numerator. We will never necessarily rationalize an expression. So let's look at a couple of more simplistic examples. We'll have more complicated ones in part 2 of our pre-cal review. If I take 3x over 2 square root of x and I want to rationalize the denominator, that means I want to multiply appropriately so the denominator no longer has a radical. So I take my expression, 3x over 2 square root of x, and I ask myself, what can I multiply this denominator by to make the radical, quote, go away? Well, if I multiply the square root of x by itself, that'll give me the square root of x squared, and the square root and the square, they're opposite operations, and I have an identity operation. So I'm going to do exactly that. And if I choose to multiply the denominator by the square root of x, I must also multiply the numerator by the square root of x. When I choose to multiply, I have to find a way to multiply by 1. Multiplying by 1 is the only way to not change your expression. So what you do to the denominator, you must also do to the numerator. So I'm going to multiply both numerator and denominator by the square root of x. And you can see here, 3x times the square root of x. We just write them all together. 2 square root of x times the square root of x will be 2 square root of x squared. And as we discussed, the square root of x squared will give us x, and so my numerator stayed the same, 3x square root of x, divided by, now my denominator is 2x. I've simplified this by canceling my x's. Cancel this x, cancel that x. I'll have 3/2 square root of x. If you prefer, you could write it as 3 square root of x all over 2, and that is equivalent and should be completely acceptable. If I rationalize the numerator of this expression, 5 cube root of x over 4, rationalize the numerator. So I'm going to multiply appropriately so my numerator no longer has a radical. Remember, a cube root takes groups of 3. Currently, I only have 1 x under the cube root, so I need 2 more to make a group of 3. So I'm going to multiply my numerator by the cube root of x squared, so I have to multiply my denominator by the same thing. When I multiply the numerator, cube roots, so I can multiply inside, so I have x times x squared gives me x cubed inside the cube root. The 5 is still there, and I write the 4 times the cube root of x squared in my denominator. Now we multiplied by the exact right thing, so that the cube root and the third power, opposite operations, give us the identity, so that gives us our x value. 5x over 4 cube root of x squared is the rationalized version of our original expression. Notice that the denominator has a radical and I rationalize the denominator. It tells me my numerator is going to end up with a radical. If I rationalize the numerator, generally my denominator ends up with a radical. So it depends on what we're doing, why we rationalize one or the other. Operations with algebraic expressions. Always remember the order of operations, PEMDAS. That is parentheses, exponents, multiply, divide, add, and subtract. When you add and subtract, you can only combine alike terms and the variable parts stay the same. So 3x and 4x, great, that's 7x. But 3x and 4x squared, one's an x squared, it's different, you can't combine them. When you're adding or subtracting fractions or rational expressions, you have to have common denominators before you can combine. So addition and subtraction, a little more restricted. You got to be same stuff for add and subtract, and that's why we teach little kids that first. When you multiply or divide, it's a little more sophisticated process. Your exponents on variables could change. You don't have to worry about like terms with common denominators and things like that. So adding and subtracting, we look for sameness in order to combine. Multiplying and dividing, it's not necessary. Here's some useful product formulas. If you want to memorize these, feel free. It's the square of a binomial, a plus b, or the square of a binomial, a minus b. Here we have what are called conjugates. When I multiply two conjugates, I get the difference of squares. And if we go backwards on this idea of a product formula, we have factoring. Factoring is the process of expressing an algebraic expression as a product of other algebraic expressions. If we try to simplify it, right, if we want to factor the number 6, we could write it as 6 equals 2 times 3. This is very similar to 6 divided by 2 equals 3, but in division, we no longer have the 6 or the 2 and just, ooh, 3, where'd that come from? But when we write it as factoring, we can see what we started with and what makes it up. So, if we want to find the greatest common factor of this really wicked exponential, it's an exponential expression, we look for the common factors of the number parts. 2 and 6 have a 2 in common. I'm looking at the variable parts. This variable part is y. This variable part also has a y. So they have the y in common. And then I notice this whole e to whatever, it's the same. E to the xy squared is the same for both of them. And so if I put these together, I have my greatest common factor of 2y e to the xy squared. And I can rewrite that down here, factored out. That's like, 6 divided by 2. I'm taking each of these expressions and I'm dividing by 2y e to the x squared. So 2 divided by 2 is 1. Y divided by y is 1. E to the xy squared divided by e to the xy squared is 1. So when I take this first expression and I divide by this greatest common factor, I get 1. Same thing for my 6xy cubed e to the xy squared. If I divide by my greatest common factor, this is what remains. So I've factored my expression by taking out the greatest common factor. As with multiplying, we also have product formulas that are used in factoring. The difference of two squares is huge. We'll use this a lot, and I will refer to x plus y and x minus y as conjugates. Conjugates, for binomials, a conjugate is what you get when you change the sign in the middle. Right? So if you have x plus y, its conjugate is x minus y. You just change the sign in the middle and you're good to go. We also have perfect square trinomials, which we saw a couple slides ago. It's just written in the opposite order. The sum and difference of cubes, again, great for a note card. Get familiar with them, but the type of society we live in today, you should be able to look that up quickly, unless your professor tells you you have to memorize it for exams. Roots of polynomial equations. The roots of polynomial equations are precisely the values of x that satisfy the given equation. One way to solve is to factor the polynomial. I knew I didn't get all my errors. One way to solve is to factor the polynomial completely and then use the zero factor property to solve. And what's the zero factor property? The zero factor property tells us if we have an equation equal to 0 and we factor it completely, then the property states one of the factors had to be 0, or both of them could be 0. And 0 is special. Think of a number like 9. If you multiply two numbers together and get 9, did one of them have to be 9 to start with? No, you could have 3 times 3. Think about 60. Think about all the different ways that you could make 60 by multiplying two things together, or more. 0 is special. Get it equal to 0, then factor, and the property says either the first factor is 0, or the second factor is 0, or some factor has to be 0, or maybe all of them are. And finally, we have the quadratic formula. For polynomials of degree 3 or higher, the problem of finding roots can be challenging, but that's what we have college algebra or pre-calculus for. And hopefully, you've already seen this and seen that technique. If not, check out my Math 1508 videos, pre-calculus videos, and that will remind you of how to find roots. For polynomials of degree 2, for quadratic equations, we can use factoring, which will work many times, but the quadratic formula works every time. Get it equal to 0, your quadratic equation equal to 0, write in decreasing order, so ax squared plus bx plus c, x squared and then x and then constant terms. And then the quadratic formula, as long as a is not 0, will give you the roots of the polynomial equation. Keep in mind you must always start with 0 and that you have your a, b, and c in the correct order before you start just randomly plugging into the quadratic formula. That's it for PreCal Review 1. If you want to know more about our review, check out PreCal Review 2.